Welcome back, Cubs. In this video, we're going to be taking a look at Lecture 10.3. Just a reminder that Chapter 10, Section 2 review questions 2 and 4 are due by 3 p.m. this evening. So let's get into Lecture 10.3 on solids. Brief lecture today. Here we go, solids. Solids, they have a definite shape, definite volume. The particles are more closely packed together than in the liquids and the gases, which means that while there's still, empty space within the atoms themselves, between the particles within a solid, there's a lot less empty space between the actual particles. So the intermolecular forces have much greater play in solids. Really the only movement there is going to be vibrational movement of the atoms themselves. You can't feel that with your finger, but in the lab, you can get some very sensitive equipment to measure that vibrational movement. Solids are much more ordered than the liquid and gases. Remember, in liquid and gases, the particles are going to be moving about pretty freely there, especially with the gases with all that empty space there. There's two types of solids that we're going to discuss, crystalline solids and amorphous solids. Remember, if there's a term in science that you don't know, break it up into usable parts that you're familiar with. So A meaning without, morph is shape, so without shape. So crystalline has an ordered arrangement, amorphous, it's a random arrangement. We can determine the strength of the attraction between the particles within a solid by measuring the melting point. So the melting point, this is the temperature at which the kinetic energy is great enough so that it can overcome the attractive forces between the particles. So it's going from a solid to a liquid because of the increase in temperature, the increase in kinetic energy. And amorphous and supercooled liquids, they don't have a defined melting point. It's more of a range. And some of these can flow over several temperature ranges and then kind of cool back into a solid. So solids, they're very dense and they're incompressible. It's pretty difficult to try to compress a solid substance versus trying to compress a balloon filled with air. Why? That goes back to the kinetic molecular theory dealing with gases. The particles aren't randomly moving about in a solid. They're kind of in a fixed position with great attractive forces between the two, leading to incompressibilty. They also have a very low rate of diffusion. So gases, they have the highest rate of diffusion. Liquids are kind of in the middle. And then solids, they have a very, very low rate of diffusion. We're talking about a few atoms per 100,000 years, long time. So a few atoms will diffuse, but they won't mix together like they would if it was a liquid or in the gaseous phase. So crystalline solids, there's 4 types. We've covered a lot with the ionic crystals. So sodium chloride, for example, when we had those 7 sodium atoms and 7 chlorine atoms to give us the formula unit of NaCl, it's a combination of cations and anions together. That would be an ionic crystal. And we have covalent network, metallic metal, and covalent molecular. So these are all the 4 types of crystals. They're made up of unit cells. So go back to the naming of ionic compounds. We discussed how the formula unit, was the correct nomenclature for identifying an ionic compound. And that's because they're made up of series of these units. And the particles are arranged in a geometric repeating pattern. So that means if you were to hit a crystal, it would shatter, it would cleave along those particular lattice lines or cleavage lines. The other type of solid that we're going to be discussing is the amorphous solid, which means without shape. So the particles in an amorphous solid, they're not arranged in a regular pattern. An example of this would be glass or plastic. So plastics, these are molded at high temperature and high pressure, but they don't have that same crystalline shape that we see with the crystalline solid. If you are viewing this video, you are firsthand looking through an amorphous solid. So some recent applications of some amorphous solids are some of the digital displays on some of our electronics, also found in solar panels. So that's what we have for the solids lecture. Please let me know if you have any questions, and have a great day, Cubs.